Hello, welcome to Special Relativity, Part 2. Let's start with what we said so far. So we said that everything calibrates space and time by using the same procedure with the same tools. So to calibrate space, we look at a certain type of word line. And this word line is in a constant relation with our word line, Bob's word line in this case, which means that the information that we get from this word line is always the same. And this specific information that we get is indicative of a certain distance from our word line. To calibrate time, we look for a word line that has a repeating cycle. And this repeating cycle is in the direction of Bob's time, which is parallel to its word line. The changes that Bob feels are along its word line. So its time is parallel to its word line, and we need to find a cycle in this direction. Once we have such a calibrating tool, which we call a clock, we can identify specific points on it that happen at a constant interval. And we use them to calibrate our time. So for example, between this green point and this green point, which we can identify on our word line, because we get the same information from our clock at these points, so we can define the difference between them as being 1 second. Now, because everything uses the same method and the same calibrating tools, the meaning of 1 second is the same for all, and the meaning of 1 meter is the same for all. However, to complete the calibration for space, we need to define the points that make it up. And that is done by defining simultaneity. Simultaneity is points happening at a thing's same time. And to define it, a thing sends information that is reflected back to it from another thing, and the point of reflection and the point on the sending thing's word line that is halfway between the sending and receiving points happen at the same time. This is with the assumption that it takes information the same time to get to the reflection point as it takes it to return from it. Now for each thing, these procedures define a coordinate system. So to define simultaneity, we send information that is reflected back to us. And under the assumption that it takes the same time for the information to get to the reflecting thing as it takes it to get back to us, the middle point between sending and receiving the information happens at the same time as the reflecting point. So these two red points happen at the same time. And to define space, we look for all the points where the procedure gives us the same middle point between sending and receiving the information. And this blue line is all these points which define Bob's space at this time on its word line. Let's call it time 1. In a similar manner, a procedure that gives us a different middle point between sending and receiving the information. So we get this middle point over here that happens at the same time as the reflecting point. And all the points that give us this middle point between sending and receiving information define the space at this time. So this is Bob's space, and we'll call it time 2. Note that in actual reality, we have 2 more dimensions. So space is defined in two more directions, and this means space is three-dimensional. So here we have two world lines, Bob and Alice, together, and each one of them, using the same type of instruments, makes its procedures and gets its coordinate system. So Bob has the green coordinate system, and Alice has the brown coordinate system. And the question that we asked and we want to answer in this video is, how do the coordinate systems relate to each other? Now, to answer this question, we'll start by translating some of our outside view to our inside perspective. Here we have Bob and world line number 1. And this is Bob's space at time 1, Bob's space at time 2, and Bob's space at time 3. And the interval between time 1 and time 2 is the same as the interval between time 2 and time 3. We can see that the distance between Bob and particle 1 is always the same. It is the same in time 1, time 2, and time 3. So particle 1 is not moving in relation to Bob. It has zero speed in relation to Bob. Now if we look at world line number 2, it has an angle between it and Bob. And if we look at what happens between time 1 and time 2, then we see that the distance between Bob and particle 2 grew by this red segment over here. Now, if we look at what happened between time 2 and time 3, then again we see that the distance grew by this red segment over here. So over a certain amount of time, the distance between Bob and particle 2 grew, which means it is moving away from Bob and it has a speed away from Bob. The speed value is this red segment distance over this amount of time. And as you can see, these two red segments have the same distance. We can prove this out of geometrical considerations that we won't really get into in this video series. But in this case, these two triangles are similar. So over the same amount of time, the distance grew the same amount, which means the speed is the same. From this we learn that a straight world line means constant speed. Now we look to world line number 3 that has a bigger angle between it and Bob's world line. And again we check what happened between time 1 and time 2. And the distance grew by this brown segment over here. And we check what happened between time 2 and time 3. And again, the distance grew by this brown segment. And these two brown segments are the same size as we said. World line number 3 is a straight line, which means a constant speed. So the distance over the same amount of time grows the same amount. But now if we compare the brown segments to the red segments, we can see that the brown segments are longer, are bigger. This means that over the same amount of time, the distance grew a bigger amount for particle 3. And this means its speed moving away from Bob is bigger than particles 2 speed moving away from Bob. As we said, the value of speed is how much space is covered in amount of time, and the angle between the world lines reflects this. However, it is important to notice that it is not the absolute value of the angle. So if we look at this segment over here, this is the growth in distance over this amount of time between time 2 and time 3. and we move it to the other side, so it's the same distance. And now we look at world line number 4. Then the distance between particle 4 and Bob decreased by this brown segment over this amount of time, which means it has the same speed as particle number 3. The difference is that particle 3 is moving away from Bob and particle 4 is moving towards Bob. And we can see that the angle between Bob's world line and world line number 3 is smaller than the angle between Bob's world line and the world line number 4, even though the value of the speed is the same speed. So for the same value of speed, the angle moving away from Bob and the angle moving towards Bob are not the same. And if we think about a different world line with a different angle, which means it has a different direction for the line of simultaneity for its space, and this means that it has its own coordinate system, then the value of this brown segment could be different. And the value of this distance is part of the value of the speed. It's this distance divided by this time. So again, the same angle value can represent two different speed values. But nonetheless, the angle between the world lines tells us about the speed. So within this same region over here, a bigger angle is a bigger speed. And within this range over here, again, the bigger angles represents the bigger speed. Now note that in actual reality, we have 2 more dimensions. And this means the world lines have an orientation one in respect to the other. So speed also has a direction. And the value plus the direction is called velocity. So speed is the value and speed plus direction is velocity. Now let's look at the same situation with the difference that world line number 1 is no longer a straight line. Again, we look what happens between time 1 and time 2. So in this time interval over here, and we see that the distance between Bob and particle 1 grew by this red segment over here. So it has a certain speed away from Bob. And we check what happens between time 2 and time 3, which is the same time interval. And we see that the distance grows by this brown segment over here, which means again, between time 2 and time 3, particle 1 has a speed away from Bob. But now if we compare the red segment and the brown segment is bigger, it's longer, which means the speed of particle 1 away from Bob grew as we move along Bob's time. And this means that a curved world line equals acceleration. Acceleration is the change of speed with time. Again, note that in actual reality we have 2 more dimensions. So again, the world lines have an orientation, one in respect to the other, and this means that acceleration also has a direction. It's not only a value, it also has a direction. Now let's notice a feature of information tracks. So here we have Bob, and here we have Bob's space at a certain point of time. And these are the 2 information tracks of our model that exist and go through this point of time on Bob's world line. Now if we look at the angle between Bob's time, which is parallel to the world line, and Bob's space, then this angle is split in half by the information track. This angle over here is equal to this angle over here. And if we look to this information track, then again, it splits the angle between Bob's time and Bob's space in half. So this angle is equal to this angle. Again, we can prove this out of geometrical considerations and show that this feature is the result of how we define space by using the assumption that information sent from our world line takes the same time to get to a reflecting point as it takes it to return back to our world line. And this assumption and the simultaneity line that we built using it, which we call space, tells us that an information track is always half the angle between the space and the time that we look at. So if we look to Jack's time and space, then again the information track splits the angle between them in half. So this angle is equal to this angle, and again splits the angle between Jack's time and Jack's space in half. So this angle is equal to this angle. And again, if we look to Alice, this is also true for Alice. The information track splits the angle between Alice's time and Alice's space in half. And over here also. So this is true for all. For Alice, for Bob, for Jack, for any straight world line. Now we use the assumption that information has the same speed value in both directions, that it takes the same amount of time to get to a reflecting point as it takes it to get back. But nonetheless, let's check that that is the case. Here we have Jack and Jack's space at this point of time, and Jack does his calibration procedures and defines this arrow as being 1 unit of distance, and defines this red arrow to be 1 unit of time. Now we have these two information tracks that start at this point on Jack's world line, and let's see where they are after 1 second. So this information track is at this point, and this information track is at this point. Let's start by figuring out the speed of this information track. So it moved 3 units of distance in 1 unit of time, which means the speed, according to Jack, is 3 units of distance over 1 unit of time. Now let's check the speed of this information track. Again, we can see that its distance is 3 units of distance from Jack after 1 unit of time. So again, according to Jack, the speed of this information track is 3. And we get what we expect, that the speed of information is the same in both directions. Let's check another scenario where Bob sends information. So here we have Bob, and this is Bob's space at this point of time, and this is Alice's space in this point of time, and we have an information track that originates from this point of time on Bob. Now from Bob's eyes, the information has speed away from him, and as we mentioned, it's the half angle between Bob's space and Bob's time. So again, there is an angle between Bob's world line and the information track, and it's the half of the angle between Bob's time and Bob's space. Now let's move to Alice's eyes, and from Alice's eyes, Bob has speed moving away from her. There is an angle between Alice's and Bob's world lines, so this is Bob's world line, and this is Alice's world line, and there is an angle between them, which means there is a constant speed between them. Bob is moving away from Alice. And from Alice's eyes, the information that Bob sends also has speed away from her. There is an angle between the information track and Alice's world line. And again, this is half the angle between Alice's space and Alice's time. So this angle over here is equal to this angle over here. And this means that both Alice and Bob see the information Bob sends as half the angle between space and time. They see the information track behaving in the same way, moving away from them at half the angle between their time and space. Now Alice sends information. So Alice sends the information over here that starts from this point over here. And again, it's the half angle between Alice's time and Alice's space. This means that the speed of information sent from a moving thing, moving in our eyes, our reference frame. So in this case, Bob is moving in Alice's reference frame, is the same as the speed of information sent from us, in this case, Alice. And if we duplicate this exercise to other world lines, then again we will see that Alice sees the speed of information the same way as the half angle between its space and its time, no matter who sends the information. This means the speed value of information is fixed. So no matter who sends the information, in Alice's eyes, the value of the speed of information is the same. It's always the same value. And this is true for any straight world line. So we can do this from Bob's point of view and see that the information that Alice sends is half the angle between its time and space. So according to Bob, we get the same thing, that any information track, no matter where it originates from, has the same speed. Let's have a short summary. We saw that information behaves the same for all straight world lines. It splits the angle between their own individual time and space in half. And we saw that for any straight world line, the speed value of information is fixed. These attributes make the speed of information the right candidate for a calibration tool, meaning that the fixed value should be the same for all. So it is something that is the same for all straight world lines, and therefore it should be the same for all straight world lines. But as we mentioned, the real reason is actually deeper than this. This is just a manifestation that this actually is the case. And the deeper reason is that the same calibrating clock and stick transfer from one straight world line to another in such a way that when we measure the speed of information with them, with these clocks and sticks, we get the same value. And the reason for this is that information is the creator of change, which means the clock and stick are transformed or changed from one straight world line to another by how the information, the agent of change, acts on them. Now, information creates change in the same way for all. It wants to change the trajectory of the world line to its trajectory, which exists in reality. So it doesn't matter what world line it encounters, it always wants to change its trajectory to the trajectory of the information track. This means that because information acts on the clock and stick in the same way, when we use the clock and stick with our assumption, they reflect this. They reflect the fact that information is the same. And this reflection is that the speed value of information is the same for all straight world lines. What we're saying is that the calibration of space and time of different straight world lines gives us the same value for information's speed. And this is the answer to our question about the relation between coordinate systems. Here we have a situation where Bob sends information, it is reflected back to him, and he receives it back at this point on his world line. Now let's calculate the speed of information according to Bob. So the information traveled in Bob's space to the reflecting thing and traveled back. So this is the distance the information traveled, twice this arrow over here. And it traveled this distance over this amount of time, the time between sending the information and receiving it back. So the speed of information according to Bob is 2 times this distance divided by this time. Now let's do the same thing, but from Alice's point of view. Try to figure out the speed of information according to Alice, using this same procedure. So the distance the information traveled is from Alice all the way to the reflecting point and back, but the information did not start from Alice, it started from this point, so we have to deduct this distance over here. And it also did not return all the way to Alice, so we have to deduct this distance over here. So all in all, we have 2 times this distance minus this distance plus this distance. And this total distance that the information traveled from sending to receiving it back occurred over this amount of time, Alice's time. So this is when the information was sent according to Alice at this time, and this is when the information was received back according to Alice. So here we have this calculation, 2 times the big arrow minus the starting point and ending point together, divided by the time between sending and receiving the information. And according to what we said, this calculation and this calculation are equal. And this equation tells us what is the relation between different coordinate systems. So it forces a certain relation between Bob's distance and Alice's distance, and Bob's time and Alice's time. Now let's see an actual example of how Alice sees Bob's coordinate system and how Bob sees Alice's coordinate system. So this is Alice world line, and this is Alice's space at this point of time, and this is Bob's world line, and this is Bob's space at the same point of time. And this is an information track that exists in reality. So this is Alice's time parallel to its world line, and this is Bob's time parallel to its world line. Now Alice does the procedures we talked about and defines this point over here as being 1 unit of distance in its coordinate system, and this point over here being 1 unit of time in its coordinate system. And according to this, we can see that the speed of information is 1. The information travels 1 unit of distance over 1 unit of time. Now Bob does the same procedure using the same calibration tools, and he gets that this is 1 unit of distance, and this is 1 unit of time in its coordinate system. Now, the fact that we mentioned before, the correlation between the two coordinate systems, has a geometrical meaning, and the meaning is the following. If we look at this 1 and 1 rhombus in this coordinate system, then its area needs to be the same as this 1 and 1 rhombus in the other coordinate system. This is the geometrical equivalent to the fact that no matter who sends the information, everybody sees the speed of information the same way. So if this area is equal to this area, this requirement is satisfied. Now let's see how Alice sees Bob's 1 second and how Bob sees Alice's 1 second. So if we look at Alice's coordinate system, then we want to know how much time is this point in Alice's coordinate system. And to do that, we go along a parallel line to Alice's space until we hit Alice's world line and see what number we get. And in this case, this is 1 unit of time, 1 second, and this is 2 units of time, so this is 2 seconds. So from Alice's point of view, Bob's 1 second is 2 seconds. It doesn't see it as being 1 second, it sees it as being taking 2 seconds to happen. Now let's try to see how Bob sees Alice's 1 second. So this is Alice's 1 second, and we go along a parallel line to Bob's space. So parallel line to Bob's space, and we hit Bob's world line at this point over here. And again, we can see that this point is 2 units of Bob's time. So this is 1 unit of Bob's time, and we double it and we get to this point over here, which is how much time passed according to Bob for Alice's 1 second. This means that Alice sees Bob's 1 second as taking 2 seconds, and Bob sees Alice's 1 second as taking 2 seconds. So they see each other's seconds in the same way, as if they take double the time. Now let's try to see how they see the other coordinate system's distance. But I remind you, for a distance, we also needed to define simultaneity. So the distance of something according to Alice has to happen at the same time according to Alice, and the distance according to Bob is 2 points that happen at the same time according to Bob. Okay, so here is 1 unit of distance according to Bob. Let's call it a stick of 1. But again, we want to remember that we want to see the distance between 2 points that happen at the same time according to Alice. So we have to find out at what point this beginning, so where this point is, in such a way that Alice will see the beginning of the stick and the end of the stick at the same time. And this is this section over here. This is the end point, and this is the starting point, which was along Bob's world line, so it remains along Bob's world line. So this is Bob's world line at the same time according to Alice as this point, which is the end of the stick. And as you can see, the distance of this 1 unit stick according to Alice is half the distance of its 1 unit of distance. So Alice sees 1 unit of distance of Bob as being half a unit of distance of hers. Now let's do the same the other way around and see how Bob sees this stick, which is 1 unit of distance according to Alice. So this is the end point. And again, we need to find the starting point, which is at Alice's world line, in such a way that these 2 points happen at the same time according to Bob. So this is the distance over here from Bob's point of view. And again, you can see that this distance over here is half the distance of Bob's 1 unit. So again, from the point of view of Bob, 1 unit of distance of Alice is half a unit of its distance. Now the exact number of how one world line sees the coordinate system of another world line depends on the angles of the world lines in reality. And I just chose specific angles, so we get a convenient conversion of 1 to 2. So each coordinate system sees the other coordinate system's time as double of its own and half the distance of its own distance. Now if we add Jill's world line over here, then again the requirement will be that the area of this rhombus will be the same as the area of this rhombus will be the same as the area of this rhombus. So once we define the coordinate system for Alice, for example, as this being 1 unit of time and this being 1 unit of distance, then we have to look for a rhombus that has the same area as this rhombus over here of Alice. Once we have this equal area rhombus, then we know that this point over here is 1 unit of time and this point over here is 1 unit of distance in Jill's coordinate system. And again, we look for a rhombus that has the same area as Alice's area. And once we have this rhombus, then we know that this point over here is 1 unit of time and this point over here is 1 unit of distance in Bob's coordinate system. Now let's do the same procedure as before and see how Jill sees Bob's coordinate system and how Bob sees Jill's coordinate system, but we will do it only for the time component. So here we have 1 unit of time according to Bob, and we want to see what this means in Jill's time. So we go along a parallel line to Jill's space until we hit Jill's world line, and this point over here is how much time Jill sees is passing for 1 unit of time of Bob. And as you can see, it's bigger than its 1 unit. And if we go the other way around, this is 1 unit of Jill's time, and we want to see how Bob sees it. So we go in a parallel line to Bob's space, and we hit Bob's world line over here, which means this is the amount of time that passed according to Bob for 1 second of Jill. And again, you can see it is bigger than 1 unit of time of Bob. It is over here, it's over its 1 second, 1 unit of time. So both Jill and Bob see the other coordinate system 1 second as being more than their 1 second. And the exact number depends on these 2 angles of Jill and Bob in reality. And this is for what we defined over here, that information tracks are at the 45-degree angle to our outside perspective, and that the speed of information is 1. Information covers 1 unit of distance over 1 unit of time. for all of these, and also for Jill. Let's summarize what happened. We used the same procedure for calibration. So we identified the same thing under the same situation and use it in the same way, which means the meaning of 1 second is the same for all. The amount of stuff that can happen over 1 second of each individual world line is the same. And the meaning of 1 meter is the same for all. So the same amount of stuff can be placed in 1 meter for each individual world line. Now we expect that having the same meaning translates to being the same. However, the way reality is, namely that information tracks exist, combined with the way we see reality, create an experience where, although 1 second has the same meaning, it is not necessarily the same. When I look at your second that has the same meaning as my second, the same amount of stuff can happen in this second, then if there is movement between us, angle between the world lines, then I will see your 1 second as taking more than my 1 second. And at least for me, this was surprising. And if we look even to the broader picture, then we said that there is a specific reality that we experience in a specific way. And these facts forced us to calibrate our ongoing change in a specific way. This specific way dictates a certain relationship between different coordinate systems. In the next video, we'll keep exploring this relationship between different coordinate systems, look at common statements about special relativity and how they appear in our model, such as the speed of light being an upper limit for speed, and try to point out some easy misunderstandings that can happen when thinking about special relativity. So what special relativity says and what it does not say.